Today, the topic of discussion is on basic concept of strength of materials, that is Module 1, Part 6, PCME 403. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering of Swami Vivekananda Institute of Science and Technology. So, in this video, we will discuss principal stress and principal planes and Mohr cycle. Now, what is complementary stresses? If we consider the stresses on oblique plane YY plane, that is, this is the Y and Y, this is Y. If you see the diagram, this is Y and this is Y, which is perpendicular to the previous plane YY. So Y dash Y dash, so this is the YY and this is the Y dash Y dash. Okay, so this Y dash is perpendicular to YY. The stresses on this plane are known as complementary stresses. That means the stress that is perpendicular on the previous plane, so the stress that is exist on this plane, that is called the complementary stresses. So in the case of normal, so that should be the complementary normal stress, that is sigma n dash, so if you see the diagram, so this is the sigma n dash, that means that plane, the stress that is on this plane, that should be the sigma n dash. So this is the sigma n dash, that is the normal. Similarly, the complementary shear stress, that is tau dash, so that is the tau, this is the tau dash, so that shear stress that is exist on this YY plane, that is tau dash. The following figure shows all the four stresses, so that means the normal stress, shear stress, as well as the complementary stresses, normal as well as shear. To obtain the sigma n dash and tau dash, we need only to replace theta y 90 plus theta. That means if we just increase the angle and we add the 90-degree with the existing angle, so that plane we obtained, that is, this is the plane we obtained. So this is the previous one, that is, and if we just rotate that, so that should be YY. So this is the Y dash and this is the Y dash. Okay, so this is the Y dash and this should be the Y dash. So this is 90 theta plus 90, that should be the angle. So we are getting that value, that means the tau dash and as well as that is the sigma n dash. So these two should be the complementary stresses. One is the normal stress, normal complementary stress, and another is the complementary shear stress. So the angle theta plus 90 is known as the aspect angle. So this is the aspect angle. From this diagram it is clear. Now it is very clear that, so sigma n dash is nothing but, we just change the angle 90 plus theta. If we just add 90-degree with the existing angle, we are getting the value of that. So that should be p by a sine square theta. And tau dash is nothing but same phenomena, that should be the minus p by 2a sine 2 theta. So if we just add this complementary normal stress and this normal stress, this is the normal stress and this is the complementary one, so we are getting this value. Similarly, tau dash equals to tau, that means the complementary shear stress and the complement and this shear stress both are same in magnitude but opposite in nature, that means opposite in direction. So that's why the complementary shear stress are always equal in magnitude but opposite in sign. Now the sign of shear stresses. The shear stress tau on any face of the element will be considered positive when it has a clockwise moment with respect to the center inside the element. If the moment is counterclockwise with respect to the center inside the element, the shear stress is negative. Now if you see the diagram, so this is the clockwise in nature, so this is the tau, so this should be the clockwise in nature, and this is also the clockwise in nature. That means the direction of shear stress is like this, that is the positive. Similarly, in the same fashion, same phenomena, that should be the opposite, that means the anti-clockwise in nature. So similarly, this is anti-clockwise in nature. That means the direction of the shear stress is like this, so that should be the um, one is positive and another one is negative. Now let us take an example. So this is a prismatic bar of 500 square. So this is in the diagram. Cross sectional area is actually loaded with a tensile force 50 kilonewton. So this is the tensile force 50 kilonewton. Determine all the stresses acting on the element which makes 30-degree inclination with the vertical plane. So we have to calculate that. Determine all the stresses. Now let us discuss. So take a small element ABCD. So this is the small element ABCD inside the member, and it is in 30-degree with the plane as shown in the figure. So this makes an angle 30-degree with this plane, and the area of cross section A is nothing but 500 square. So the tensile force is that is here, it is given, that is 50 kilonewton. So the normal stress on 30-degree inclined plane, that is sigma n p by a cos square theta. So we just put the value of p, value of a, and value of theta we are getting. So this is the exact value, that is sigma n. Similarly, the shear stress on 30-degree plane, that is tau, is nothing but p by 2 sine theta. We just put the value in this formula and we are getting, so value of p, value of theta we know, and value of a is also known, and just getting the value of the shear stress tau. Similarly, complementary one, that should be the value of the complementary, that is the angle should be, aspect angle should be 90 plus 30, that is 120 degree. Now the normal stress on 120-degree inclined plane, that should be the sigma n, that means the complementary normal stress. So this is, we just put the value and we are getting this. Similarly, in the same fashion, so the shear stress on 120-degree inclined plane, that is tau dash, that should be p by 2a sine 2 theta. Here theta equals to 120 degree, and we are getting, that is minus 43.3 MPa. That is, negative means the counterclockwise. Now that is the state of stress on the element. So if we just plot all the stresses on the element, so that should be looks like this. That is sigma n, that is the direct stress on that plane, that is the sigma n, and this is the tau. This is the tau. The tau value is minus 43.3, and tau dash equals to 43.3, that is tau dash and tau dash. And similarly sigma n dash, that is 25 megapascal, and this is the complementary normal stress, and this tau dash is the complementary shear stress. So all these are plotted in the ABCD element. Now the material subjected to combine direct and shear stress. So if you see the diagram, so this is the three-dimensional view, and if we cut that element and ABCD part, so if you see the diagram, this is the, on that is the normal stress, and this is the shear stress, and this is the angle theta, and each side, that means each plane carrying these stresses, one is the direct stress, another one is the shear stress, and similarly this is direct stress, this is shear stress, this is direct stress, this is shear stress. Okay, so there are two suffix, one is the one is indicating the direction plane, first one is indicating the plane, and second one is indicating the direction. So this is the y plane, x direction, this is the x plane, y direction. Okay, similarly so this one is the normal stress, and this is the shear stress acting on along this plane. Now sigma x and sigma y are normal stresses and may be um, tensile or compressive. So we know that the normal stress may come from the direct force or bending moment. So tau xy is the shear stress. We know that shear stress may come from direct stress from the torsion, that is tau xy and tau xy. So tau xy and tau yx are complementary. So these two are exactly same in magnitude, but the uh, opposite in sign. Now let sigma n is the normal stress and tau is the shear stress on the plane at an angle theta. So consider the equilibrium of the element, we can easily get. So this is the sigma n value, and this is the tau value, that is the shear stress value, and this is the sigma n value, and above two equations are coming from the considering equilibrium. So this is the sigma n value and this is the tau value, and we are getting this. Now location of plane from the plane of maximum stresses. So this is the normal stress sigma n. So sigma n. So how will you get? So if we just derivative the sigma n, that is we are getting the value of uh, this angle. Similarly, shear stress tau max, how we'll get? So the tau for tau max or tau maximum or minimum, we just derivative that tau. So that is equals to 0, and finally we are getting the value of that angle. Now let us discuss an example. So this is the at a point of a crankshaft, the stresses on two mutually perpendicular planes are 30 MPa and 15 MPa. That is, those two are tensile. The shear stress across the plane is 10 MPa. Find the normal and shear stress on the plane, making the angle 30° with the plane first of first stress. Find also the magnitude and direction of the resultant stress on the plane. Now that is the sigma x, we know that this is the value, sigma y is no value, tau xy is the value. Okay, so these are all given. So the normal stress sigma n should be, just with the help of this formula we are getting, just putting the value sigma x and sigma x and sigma y, also angle theta. So we are getting this value, that is the normal stress. Similarly, shear stress tau, so it is with the help of the formula, and we just put the value and we are getting 1.5 MPa. Now similarly, the resultant stress, that is sigma r, is nothing but that is the root over of these two, and we are getting this value. Similarly, the angle of obliquity, that is tan phi tau by sigma n, so we are getting this value, that is the value of phi. And so in this diagram, there is the element. So what is the value of sigma x and sigma y? Sigma x, sigma x, this sigma y, tau x y. This is the angle theta, and this is the sigma n, and this is the tau, and this is the resultant, and this is the angle 2.25. So all these are plotted on this element. Thank you. Thank you very much.